Stealth technology, the internet, GPS in the palm of your hand, autonomous operation.
Technology is a driver of our times. Since its founding in 1958 in the midst of the Cold War, DARPA, the Defense Advanced Research Projects Agency, has been a driver of technology. Welcome to Voices from DARPA, a window onto DARPA's core of program managers. Their job, to redefine what is possible. My name is Ivan Amato, and I'm your DARPA host. Today, I'm pleased to be talking with Dr. Michael Fiddy, a program manager since 2016 in the agency's Defense Sciences Office. We're recording our conversation from our respective homes as we do our part to slow the spread of COVID-19, the pandemic disease caused by the coronavirus SARS-CoV-2. This is also why you might hear some ambient sounds like trucks and sirens. Prior to coming to DARPA, Mike, as he is most often known, was at the University of North Carolina at Charlotte, where he was the founding director of the Center for Optoelectronics and Optical Communications and director of the National Science Foundation's Industry/University Cooperative Research Center for Metamaterials, which are a class of materials that interact with light in the darndest ways. Mike earned his PhD in physics from the University of London, and I am just so pleased, Mike, that you're joining me.
Well, thanks for that introduction, Ivan. I'm happy to be here.
So I know, Mike, that your primary interests reside in the many ways that light and other forms of electromagnetic energy interact with matter. But before we get into those interests, I'd like to hear how it is that you became interested in science and ultimately in particularly optical-based phenomena.
As a kid, I used to play around with binoculars and magnifying glasses, polarizing filters. I was always interested in trying to understand why visible light that we could see would go through some materials like glass and not others. And I really was trying to understand what the difference between them was as a kid and what was going on that allowed me to see through a piece of glass. So I chose courses when I went to college that focused a lot on electromagnetics and light and scattering theory.
Were there any particular influences that really, sort of got you going in this? Did you have a fantastic professor? Were your parents scientists? Anything of that sort that really steered you in the direction of a professional scientist?
I think I'd have to say that my father, who was in the Navy from very young age, he ran away from home to join the Navy, always had telescopes and binoculars at home and magnifying glasses. I think I picked up his enthusiasm for imaging, bringing scenes up close to inspect them more carefully.
Wow, very interesting to hear that. And as you were saying that, it also images of the scientists from the 16th and 17th century came to mind, because glass optics, both in the form of telescopes and microscopes, really are kind of at the beginnings of the scientific enterprise. So you've got.
I'm not quite that old myself.
Not quite, but it shows the connection. So every program manager has a "How did I get to DARPA" story. I'd love to hear yours.
Okay, well I'd had some interaction with DARPA over the years, and I'd been talking to a program manager in DSO who was starting a new program that was very much in the area in which I was interested in being a possible performer. So I happened to come to the Discover DSO Day when he talked more about it, met with the then office director at that Discover DSO Day. And
I just want to interject, DSO being Defense Sciences Office, for listeners who might not know that acronym.
So I did meet with the director of the office at the time, and she suggested I might like to consider becoming a program manager, since I had all these ideas that there was no way I could be funded to do, but maybe I could find others who I could fund to pursue them. So it happened very quickly. The meeting I attended was in June, late June, I think, and I started at DARPA a couple of months later, September 2016.
You have actually quite a large portfolio for program managers. I'm not sure if it's 5 or 6 different programs, but they focus on really some rather amazing ideas, and we'll get to these in a little while. I mean, one of them that really catches my attention are things like tapping into kind of the energy of the vacuum, perhaps even for things like propulsion without fuel. As I said, we'll get to that in a little bit. I'm kind of interested in, at the moment, a more strategic level of your thinking, that informs your R&D efforts and the kinds of programs that you have ended up formulating and running. In fact, you've said, and I love this line, I am interested in electromagnetic waves and their interaction with matter from DC to daylight. So I think if you explain that to listeners, those listeners who might not know what that means, I think that they might actually have some handle on where a lot of your thinking comes from.
Well, if we really go back to basics, we're made of atoms, of charged particles, and in principle, if you accelerate a charged particle, it will radiate. And so we're completely bathed by electromagnetic fields, literally from DC to very high frequency fields.
DC being direct current.
Zero frequency. Think of it as zero frequency. So, going back to my comment about looking through a piece of glass, how does that happen? We have to think about electromagnetic waves, whether they're very high frequency of the sort we see, or much lower frequency, perhaps radio or microwave. What are those fields doing? They're carrying energy and they're moving atoms around. They're exciting atoms as they propagate. And we might want to detect that radiation. We might want to bend it or steer it. We need to understand what those interactions are at all scales in order to exploit it and make use of it. And what I'm finding is that even though electromagnetism goes back 100 years, the first radio was probably in 1895, that classical picture, which evolved to describe electromagnetic waves and their interactions, is still surprising us when it comes to trying to model the interaction of waves with structures that are perhaps of the order of the wavelength in size, or when we're trying to explain interactions where there's strong resonances or what we would call nonlinear effects. So the material properties that could be described by early electromagnetic theory, the classical electromagnetic theory, keep pulling us to test them and stretch them into new realms where we are discovering new properties, new physics, new opportunities all the time. And I think all of the programs I have in my portfolio touch on some aspect of that, whether it's detecting light, looking at these non-linear and strongly interacting relationships light can have with engineered matter, with structures that are of a similar size and of the right material properties to the wavelengths we're interested in, to managing electromagnetic waves for better imaging or sensing. We've got one program where we're looking at, instead of imaging with frequencies that we can see, you could go to lower frequencies, much lower frequencies, and start thinking about trying to image through structures with very low frequencies that penetrate. So unlike glass that I can see through, I don't expect to see through a piece of metal, but very low frequencies can penetrate a piece of metal. So can I extract information from radiation of low frequency that goes through those materials, like metal, and find out what's on the other side?
Right, and so that's mapping onto your program called Imaging Through Almost Anything, Anywhere, right?
Correct. We've become more sophisticated in how we can model the emission of low frequencies from sources, from antennas, and how we can describe how those, what we would call near or quasi-static fields, interact with matter and can then provide us information about that matter and that interaction.
Right. So this is reminding me of one of your programs, which really fascinates me. They all do, is RadioBio, right? So we're talking about, in this case, electromagnetic interactions with biological material, and in this case, I think you're really looking more on the cellular level.
Actually, that was the first program I launched. I pitched, so to speak, coming to DARPA, and it was born out of previous work in North Carolina, where I realized for some of these engineered materials to have the kind of remarkable new properties that we hadn't seen before, so-called metamaterials, it might be convenient to grow them. So I was looking at chemical methods that might self-assemble some of these resonant structures, some of these geometric-like shapes that interact very strongly with light. And it occurred to me that some of these structures occur in nature. And I got to thinking about whether nature perhaps is already making use of very subtle electromagnetic interactions between cells, between organs, between individuals, using electromagnetic waves in ways that we haven't really thought about or studied very deeply. So the program had a goal of trying to determine whether cells, or at any scale, biosystems, which we knew would be susceptible to exposure by different frequencies of electromagnetic waves, whether these structures might actually be generating electromagnetic waves, and if there could be some purposeful communication going on over larger ranges than one would expect to see with normal chemical signaling, biochemical signaling, that's usually used to describe how cells and biosystems communicate with each other. The program's still going. It's a very challenging problem, but it's quite clear that biological structures do emanate electromagnetic waves across going back to DC to daylight, in fact. But are they exploiting them for some purpose is a question we're still trying to answer. If it turns out there is this network of communication going on in biological systems for some purpose we haven't understood, then of course it opens up the possibility of perhaps being able to intervene and generate similar signals externally for positive purposes, to perhaps heal wounds, for example, if there are charges and fields involved in that process in some way. So I think it's a good area to think more deeply about, because it would be terrible to miss some opportunities for doing good if we just have not thought deeply enough about what's going on.
So I'm wondering if any of the performers, and that's sort of DARPA speak for the researchers or research groups that end up getting essentially contracts through program manager and to work on a program and try to realize some of the goals of the program. Have any of your performers discovered things and published things in this arena that have been surprising?
For a number of application areas of interest, for example, in biofilms, one performing team has established that there are a couple of frequency ranges in the terahertz where there are structures which are somewhat tuned to transmit and receive over a couple of bands, a couple of ranges of frequencies in the terahertz range.
Right, and just a couple of things, just so listeners know, a biofilm, I typically think of that as a kind of bacterial
Yes.
Carpet of some kind.
That's right, and some biofilms are extremely useful. They protect what's underneath them. We have biofilms on our lungs, for example. Some biofilms are a pain to deal with, like those that grow on the bottom of ships and have to be scraped off frequently because they just collect so much other debris. If we could identify a communication channel in the terahertz regime, which is selective to a particular biofilm that we don't want, we might be able to broadcast a set of frequencies to it in a certain way that confuses it makes it think, it was time to move on and it shouldn't continue to form a film there. That's one of the goals.
Yeah. Well, I just am fascinated by this idea of imagining that there could be, not knowing, but that there could be a kind of whole world of electromagnetic communication in kind of the cellular and biological realms that we essentially have been, blind to, and for not actually asking the question. By asking the question, you then will know what to look for, right? We'll know what signals to seek and measure.
Picking up on that, I do like to remind everyone that we all thought the Earth was flat for a very long time until we started looking more carefully. So I'm a great believer in the fact that we've been doing science for a few hundred years and there's still an awful lot we don't know.
Right. And so that reminds me of another thing that you said. This might have been at a DARPA conference called D60, which was in celebration of the 60th anniversary. It might have been somewhere else, but you said that you're looking for light matter interactions that we have missed. And certainly that is what we were talking about in RadioBio. But outside of that program, where else does that statement apply among your programs?
Well, there are a few. For example, in the NLM program called Nascent Light Matter, where nascent is supposed to imply interactions that we might have missed or not really properly understood, we're seeing that one can now engineer materials which have a refractive index close to 0. Now that's kind of bizarre because free space, vacuum, air, has a refractive index of 1 in the visible. Glass that I like looking through may have a refractive index of 1.3, 1.5. But we can make a material that has a refractive index that's close to 0. And what does that mean? Well, it's going to refract and deflect light in a very unusual way. But we're finding that by looking more deeply at models for those interactions with the material having those properties, these materials have very large nonlinearities. What does that mean? That means if I illuminate the material with frequency F, I might generate frequencies 2F or 3F. It will generate higher or lower frequencies depending on how I do it. But this, of course, is very important. For example, if night vision, if I want to convert infrared wavelengths to visible wavelengths to help me when I'm driving see better at night. This is a material now, because of its structure and properties, that's giving me a much more efficient way of doing that than I've been able to so far with existing night vision technology. That's just one example.
In that one example, though, you were also addressing another question that I had, which is, explaining how, your kind of thinking, which is to say, how do light and matter interact? How is it that asking questions like that and developing programs based on that idea, how does that relate to the DARPA mission, of furthering national security? And as you put it also at some point, that you're trying to avoid a Sputnik-like surprise based on electromagnetic phenomena. So you did point directly to the night vision possibility. Why don't you give me one more? Because you seem to have a couple more ready to hand there.
Yes. Yeah. Well, the Defense Sciences Office has a few mission priorities for the agency, and one of them is anticipating surprise. So whenever one comes across some interesting new, for me, physics or electromagnetic phenomenon, it's tempting to think about whether there could be some new capability buried in that phenomenon that could provide Department of Defense some new capability, or is it worth investigating to see whether there's actually nothing there, nothing of any consequence, at least for the next 10, 20, 30 years, so we will not be surprised by new technology based on this phenomenon. So a lot of what we do is to investigate as rigorously as we can these ideas, either to see if there's a new capability for national security, or if there's really nothing to be afraid of from an adversary pursuing this work, as far as we can tell. So, one example that has popped up a lot in the last 10 years is, are there different mechanisms for propulsion that we've overlooked that might be electromagnetic in nature, that might enable propulsion, for example, in space, but without fuel, without physically having to have fuel on board. Some ideas have been floated to do this based on electromagnetic interactions with structured materials, with resonant structures, like I mentioned earlier, or with metamaterials, where pattern structures might be strongly non-reciprocal, meaning that light will go one way through it, but not the other way. And there's some sort of foundational math associated with quantum theory, which says that there are these fluctuations in space of electric fields and magnetic fields, a consequence of quantum theory that these fluctuations occur, and they have a certain energy associated with them. Now, that energy density is not something we normally think we can tap into, but we can't rule out entirely whether one of these strongly non-reciprocal structures might be able to be deflected in some way just by it sitting there in space, immersed in these naturally occurring background fluctuations. It's probably highly unlikely, but we can't not look at this a bit more carefully just in case.
Right, and I just want to interject that I believe what you're talking about here is the focus of your Quest program. One of the ways I've heard that program described, which fascinates me, is in some ways it's investigating the possibility of accessing or interacting in some way energies that are associated with the vacuum of space.
Yes. I think the usual, one might even say, common sense view of it is that if you're already at the bottom of a well, you probably can't go any lower. And this energy background that quantum theory says we're immersed in is a sort of lowest energy state. It's a ground state. So how can we learn to somehow dip into it or surf across it or manage it in a way that we could extract some energy temporarily and put it back, or extract some momentum or thrust temporarily? It's a challenging problem. It's a question that's come up many times over the years. I would say that the time is right now where we can make structures and we can do very exquisite experiments in terms of measuring thrusts. And we have more advanced theoretical models of these phenomena. So the time seemed right to see if we could investigate more thoroughly this possibility. And if we find in 18 months' time that there's really little hope of getting any significant energy from this mechanism, so be it. We've learned something. It's important to know whether our adversaries, if they're pursuing similar lines of inquiry, are going to hit the same brick wall.
Right. Well, and what a worthy concept to pursue if there is any chance that it could ultimately be realized, because one of the greatest burdens to bear, right, in the space enterprise is hauling tonnages of fuel through the atmosphere and into orbit and beyond. So if there is some alternative to doing that, and actually, in a sense, looking at this, being in space where space itself could become part of the mechanism of propulsion, well, it would be nice to know if that is possible.
It would. And an earlier DARPA program that ended a few years ago looked at how nanostructured surfaces can manage this energy density, this vacuum energy density. And by manage it, I mean make it vary spatially across the surface so that it's possible to create attractive and repulsive forces near these surfaces. These are called Casimir forces. We have some young faculty awardees right now looking at how these forces near a surface may be sufficient to change atomic energy levels and lead to different spectroscopic signatures from atoms just by being close to these surfaces. So if we can understand more about how the forces interact with matter and are shaped by the presence of matter, we may understand whether we can extract and exploit the energy associated with these phenomena in some useful way. And that's what the program Quest is designed to do. We're going to look more carefully at what the possibilities are to do that.
June 30th is your last day, if I've got that right, after about 4 years as a program manager. And actually, that's probably about an average tenure for program managers. There's a lot of turnover by design at DARPA. So I'm just wondering, as you finish your tenure here, what you've learned about the DARPA culture and, where it fits in kind of the innovation ecosystem.
Well, it's certainly a very innovative place, and it's packed full of very bright, dedicated people. And I've been overwhelmed by the collegiality, the respect, the sense of responsibility, the strong sense of belonging to this agency, to DARPA. It really is a wonderful place to work. And, the responsibility everyone feels is that this is taxpayers' money being used to try to anticipate surprise, come up with new capabilities. So we structure our programs in a way that as you step forward through them month by month, phase by phase, we always want to feel that we're learning something of value towards that broader mission of making the country a safer place. So I've really been humbled talking to colleagues, and you may know we have service chief fellows who come in. We have off-sites where we meet with soldiers, sailors, airmen, and we listen to what's bothering them, what they see as their highest priorities. And we try and fold all of this perspective we get from being at DARPA into trying to shape, design, plan, and manage a program that is truly beneficial to our warfighters.
Well said. Thank you for sharing all of that. It also just makes me want to ask one follow-on question in this sort of the end of tenure kind of set of questions, which is, you've had all of these programs, a good handful of programs. This means that you have been working with probably a large number of research groups over the years. And I'm just wondering if there's anything particularly memorable, surprising, or poignant, that you think listeners might find interesting amongst all those interactions.
I think there's something special about DARPA in the eyes of our performers, as well as those of us fortunate enough to work for the agency. I think that rapid turnover, that sense of urgency, that very well-organized structure that DARPA has makes performers feel that they are engaged in something special when they get funded and they want to give it their best. And I do see a lot of performers who put in really a lot of extra effort to make those deadlines, keep us informed, stay on track. They understand that we're usually in an arrangement with them where, as program managers, we're in regular contact and we're involved month by month, quarter by quarter with what they're doing, and they don't want to disappoint. And they understand that the program has a goal, and the goal was approved for good reason, because it's addressing some need that the DoD has.
Right. So it's interesting that you mentioned kind of that mission-oriented, goal-oriented kind of research, as opposed to maybe what we might think of as curiosity driven, coming out of the great endless frontier model of science post World War II. I do find that dynamic at DARPA absolutely fascinating, where there is this big goal, there is a big mission, there's a potentially large payoff, and it becomes this wonderful collaboration between program managers like you and as you say, the performers that then work on your programs.
The P in DARPA is for project. And as we discussed earlier, pursuing a research project based on an idea that there could be something of value if the idea is correct is great, but that the idea represents foreseeable threats if it's correct. But we establish that the idea was bad, was wrong, that we get negative results is also extremely valuable. It's important to know what doesn't work. And this is something which in academia is, and probably in industry, I guess, not of quite such high value. But for us to know what doesn't work is just as important. And this is a different mindset, especially to explain to performers that we just want to know. They want to do their best science, their best engineering, and we just want to know, does this phenomenon occur? Is this idea correct? Does this theory predict X? And if it doesn't, that's fine too, because we've learned something as a result. That's very important.
Right. In other words, a negative result has nothing to do with failure. It's actually a success because it helps us understand the landscape of what is possible.
Precisely. That's exactly right. Yes.
Okay, Mike, last question. You're leaving DARPA. What's next?
Well, I have a couple of projects that I've got hooked by. So I will go back to the university for some of the time after I leave DARPA to teach and focus on one of them. But I'm exploring a possibility to stay up in the DC area and work on one of the others with a government lab. So nothing's completely firm yet, but it's moving in that direction. So I'm hoping to have the best of both worlds and continue to work on some of these projects that I feel are very compelling and could have some significant impact in the near future.
Well, I just want to thank you for your 4 years or so of service as a program manager at DARPA. May you have the best of both worlds. May you have a great next professional adventure. And I just want to thank you for spending this time with me.
Well, thank you, Ivan. It's been a pleasure. And I appreciate you asking me to do this. Thank you.
And thanks, listeners, for sharing this time with us. I hope you join us again for the next Voices from DARPA. Thanks also to Ben Sullivan for his partnership in producing this program. For more information about Dr. Michael Fiddy, the programs he runs in the Defense Sciences Office, and the other breakthrough technologies DARPA is working on, visit darpa.mil. And for links that enable you to download this podcast, go to the Voices from DARPA page on DARPA's website.